you very much. So first of all, I'd like to thank the organizers for giving me these opportunities, and also everybody here for coming to my talk. So my name is Takashi Imamura from Chiba University. So today, I'm going to talk about our recent work jointly with Matteo Mucciconi and Tomohiro Sasamoto here. And so we have been interested in the stochastic process, or the interacting particle systems, especially having a nice algebraic or combinatorial structure. So these structures are closely related to the Cauchy identity. So first, let me explain what it is, the Cauchy identity. So this is the Cauchy identities. So this is the summation identities of the product of two Schur functions over the partition like this. Okay. So where lambda is the y is a set of partition. The partition is the sequence of non-decreasing integers like this, and s lambda here is the Schur function. Sorry, I don't show the precise definition of these functions, but this is a symmetric polynomial of the parameter of the variable a1 through an, and this is labeled by the partition lambda like this. And so we take a sum over the product of Schur function over the partition. Then so we get a nice product structure on the right hand side. So this is the Cauchy identity. Okay. So and dividing the both hand side by this product. So this identity can be rewritten as this one, where S. So this object is defined by this form like this. So this is called the Schur measure, because this can be regarded as a probability measure on partition y, probability measure on lambda. So and these a and b is a parameter of this Schur measure. Okay. So the Schur measure, this one, plays an important role in the studies of the integrable probability. So because there are two important aspects of this measure. Okay. So one is that this measure is related to the KPZ models. So this means that the x is a certain random variable of the KPZ models. So there are several interpretations, but typically x is a particle current in the TASEP with step initial condition, or the particle position in the push TASEP with the step initial condition. And x can be interpreted as the energies of the directed polymer model or height function in some certain growth process called the PNG model. Yes. Yeah. So, So let me explain the details about these two models, the TASEP and push TASEP, like this. So TASEP is a totally asymmetric simple exclusion process. The rule is that we consider the one-dimensional lattice like this and a particle here. And this particle can hop to the right neighboring site with probability a. The particle labeled I goes to the right neighboring site with probability ai times bj, where j labels a time like this. Okay. But if the target site is empty, but if the target site is occupied like this, so in this case the particle cannot hop and have to stay here like this. This is the exclusion interaction. Yeah. So this is the TASEP, and So under this rule, we consider such kind of things. So first we consider the step initial at t equals 0. So we consider step initial condition where all particles are occupied in the negative side and all positive side are empty. And then we perform the TASEP time evolutions, and so we count the number of particles which pass through the origin. This is the particle current. Okay. So we have another model, the push T-step, like this. The push T-step is another variant of the exclusion process. So this is also a discrete time Markov chain, and so the left sequential update. Okay. So first we update the particle number 1. It is just a geometric random walk like this, where the distance obeys a geometric distribution. So, and the second particle, so forced to push by the first particle like this, and then they do the independent random walk like this, and so on. So repeating these rules from first particle to the nth particles, so the time evolution between j minus 1 through j is finished like this. So we consider we also consider the step initial conditions, and time evolution of the these models. And in this case, so we focus on the position of the nth particle like this. Okay. So we consider this kind of quantity current intercept or position of the push T-step. So this is So the probability distribution of this quantity is equal to the marginal distribution of the Schur measure on the first row. So this is the first important relations, important aspect of the Schur measure. It is related to the KPZ model here. Okay. So on the other hand, so it is there is another features of the Schur measure. This is a determinant. This is a typical model of the determinant of point process. Yes. So meaning that the mk is the k-point correlation function. Mk is the probability that some element of the partition lambda is equal to x1, x2 through xk. So this k-point correlation function is expressed as a k by k determinants, where this function k is called the correlation kernel, and in this case the correlation kernel is expressed as a product, the double integral form like this. Okay. So combining these two facts, so we have combining them, so we have a Fredholm determinant formula for the KPZ model like this. Okay. So and then the Fredholm determinant is defined as this expansion like this. And so by taking a scaling limit, and the scaling limit can be taken easily we just use the saddle point analysis, and then so we get a scaling limit of the KPZ models. And in this case, it goes to the GUE trace evidence distribution like this. So this is the very basic stories for the one of the most basic stories in the studies of the integrable probability. Okay. So and so there is a certain variant of the Cauchy identity called the Littlewood identity. Okay. So this is the Littlewood identities, and the difference between Littlewood and Cauchy identity is that in the Littlewood identity we take the summation over some special partition where the lengths of the first and second element and the third and fourth element are the same. So so we take a summation over such kind of paired partition like this, and so the summation and in the Cauchy identity, so is a summation over the product of two Schur function. But in the Littlewood case, yeah, so we take a sum of the single Schur function like this. But so this summation still has a nice product form like this. Okay? So this is the Littlewood identities. And so but we can consider a similar story to the Cauchy case. So in this case, the associated probability measure is called the Parthian Schur measure, like this. And this measure has two important features. Okay, this is also on the one hand, it is related to the KPZ models, but in this case, the KPZ model in half space. Okay? So typically, X is the position of the nth particle in push T-step is particle creation. So yeah, let me explain a little bit about the detail. Okay. So in this case, we consider we also consider the one-dimensional lattice, but in this case, we consider the half space. So we consider only the positive region here. And at t equals 0, there is no particle. And at t equals 1, so the particle number 1 is created. And the distance between between this position and the origin is random and so distributed by the geometric distribution with certain parameter. And at time t, so this particle number 1 do the geometric random walk, and then the new particle number 2 is created here. Okay. So where the distance is again the geometric distributed by the geometric distribution like this. And from t equals 2 and t equals 3, so we do the so these two particles moved according to the rules of the push T-step, okay, like this. So this is the push interaction plus random walk like this, and then the new particle number 3 is added like this. Okay. So so we repeat this procedure. So and in this So in this case, we consider the random variable x, which is the position of the nth particle at t equals n. Okay. So in the probability distribution of this quantity, can be shown to be equal to the marginal distribution of the Parthian Schur measure on the first element. Okay. So this is one important properties of the Parthian Schur measures. And on the other hand, so this Parthian Schur measure is not a determinant point process, but a Parthian point process in this case, meaning that the k-point correlation function is expressed as a k by k Parthian like this. So so we don't show the precise definition of the correlation kernel k, but the k is a certain 2 by 2 matrix kernel. And combining them, we can get a nice Fredholm Parthian formula for the KPZ model in half space. Okay. Yeah. This is another story of the integrable probability related to the Schur measure or Parthian Schur measure. Okay. Right. So, but especially before 2010. Okay. Oh, sorry. Yeah. But since 2010, so the phase of the studies on integrable probability changes in some sense. Because so there is a discoveries of the exact height distribution functions of the one-dimensional KPZ equations. Okay. So this is the KPZ equation. So this is the stochastic partial differential equation of the height function h. But in this talk, we only focus on the one-dimensional case. Okay. So okay. So this equation is first introduced by Kardar-Parisi-Zhang in 1980s the physicist. But so this equation is the stochastic, the nonlinear stochastic partial equation. So the problem of well-posedness are very important in the studies of the mathematical physics. And yeah, in 2010, so the explicit formulas for the probability distribution of the height function with certain initial condition, so have been found out, okay, by Tomohiro and Spohn, and independently by Amir, Corbin, and Krustel in 2010. Okay. Yeah, so this result can be summarized as one single relation like this. Okay. So the left-hand side here is the certain Laplace-like transform of the height function. Okay. So yeah, from this information, so one can get the probability distribution of the height function. Okay. So this quantity can be expressed as a one single Fredholm determinant like this. Okay. This is the main result of Sasamoto and Spohn and Amir, Corbin, and Krustel. Okay. So this is very beautiful relation, and this Fredholm the correlation kernel of the Fredholm determinant is expressed as this form like this. Okay. So this is similar to the GUE kernel, but the main difference is this function, and this is the Fermi distribution functions in quantum statistical physics. Okay. So yeah. So this and so this Fredholm determinant describes a certain probability of the free fermionic system of the positive temperature with the airy Hamiltonian. Okay. So the big question is why such kind of free fermionic structure appears in the studies of the KPZ equation. So this is the one big question. Okay. Okay. So and so in the previous slide, we discussed the TASEP and push-TASEP models, but we know that these models cannot access to the KPZ equation. Okay. So the question is can we construct some discrete KPZ models having a it's okay. So having a similar determinant structures. This. Okay. So can we construct a discretized version of the KPZ equation? Okay. And so I want to consider something origins of this determinant of structures. Okay. Okay. So this is the motivation of this study, and to consider this problem, so we go back to the Cauchy identity again. This is the Cauchy identities. And it has been known that there are two one-parameter generalization of these Cauchy identities. Okay. The first one is about the q-Whittaker polynomial here. So this is a one-parameter generalization of the Shur polynomial, one-parameter cube generalization of the Shur polynomial. If q goes to 0, it goes to the Shur functions. Okay. So this is the q-Whittaker versions of the Cauchy identities for the q-Whittaker polynomial versions. Okay, so and the right hand side has again a nice product structures, but in this case, the q-Pohohammer symbol appears like this. This one. This is a certain infinite product like this. The second generalization is about the skew Shur polynomial. So this is another generalization of the Shur functions like this. So to the something skew shape here. Okay. So this is the Cauchy identity like this. Okay. So in q equals 0, so both of the generalization goes to the original Cauchy identity. So in this sense, these identities are the one parameter, the two different generalization of one parameter generalization of the Cauchy identity. Okay. So and as in the Shur case, So we can consider the associated probability measure. The two types of associated probability measure. The first one is a q-Whittaker measure, like this. This is a definition. This is the probability measure on partition mu, like this. Okay. So this measure is introduced by Borodin and Corbin. And yeah, this is trivial, but if we take q equals 0, so this measure goes to the Schur measure, like this. Okay. So so by Borodin and Corbin, so we find that this measure is related to the certain KPZ model. But in this case, not TASEP and push TASEP, but a certain q-generalization of TASEP and q push TASEP. Okay. And a certain directed polymer model with finite temperature called the log gamma polymer models are also, and the O'Connell-Yole polymer model are also related to this measure. Okay. Yeah.
So for some specific value of q, or for some q in some limit, or
q is the one one parameter. The q takes a value.
Polymer model for the log gamma polymer model. Which q do you use?
Oh yeah. So in this case, so we have to take a q equal 1 scaling limit. Okay. Yeah. Yes, thank you. Yeah. And q equals 0, so this goes to the TASEP, the original TASEP and q push TASEP. All right. Yeah. So this measure is so related to the KPZ model, but unfortunately, so this is not a determinant of point process. Okay. Contrary to the Schur case. But nevertheless, so there are nice Freedom determinantal formula, so obtained by Borodin and Corbin, and others, like this. So we want to understand so why such type of determinantal formula appears in q-Whittaker measure, which is not the determinantal point process. This is one motivation of our studies. Okay, so this is the q-Whittaker measure, and another and from this generalization of the Cauchy identity, so we want to so we can consider another type of probability measure called the periodic Schur measure. This one. This measure is introduced by Borodin in 2007. And this is also the q-generalization of the Schur measure. And so unfortunately, so this measure does not seem to be related to the KPZ model. But this measure is a determinantal point process. Okay. More precisely, so so if you so consider these variables, so which is so lambda itself is distributed as a periodic Schur measures, but so if you shift this lambda by the certain independent random variable s, so this object is the determinantal point process. Okay, like this. Okay, so there are so okay, so we have a two stochastic two probability measures, and q-Whittaker measure is related to the KPZ models, but it's not a determinantal point process. On the other hand, the periodic Schur measure does not seem to be related to the KPZ model, but it is a determinantal point process. So we want to connect them. Okay, so this is our main result. Okay, so so let's look at the right-hand side of these Cauchy identities. So we notice that the right-hand side, the structure of the product structures of the right-hand side is essentially the same. Okay. Only difference is this factor. And this factor is very easy. So so from this relation, so one can easily find that this type of identity holds like this. Okay. This identity is trivial, but what we show is that this one. Okay. So this type of identity holds if we restrict the summation. So on the the first element like this. Okay. So this is the slight generalization of this identity. Okay. But this looks a certain tiny step, but this is something critical. Okay. Because so this relation can be rewritten as a relation between the marginal distribution of the q-Whittaker measure and periodic Schur measure like this. Okay, so we can connect the two probability measure in the level of the marginal distribution. Okay. So if you use this relation, so one can get the Fredholm determinant formulas for the KPZ equation. Okay. Because in the left-hand side, so this object is related to the KPZ model, and this object is the determinant of point process. And so we connect them. So we easily get this Fredholm determinant structures. Okay. So this is our main result. Oh, sorry. Okay. So now, I want to explain a little bit about how we get these relations. Okay. Okay. Yeah. So rather than showing directly this relation, so what we actually show is the certain bijection on the combinatorial object like this. The left-hand side has a 4 combinatorial object, B, W, kappa, and nu. And BW is a certain tableau called the vertically strict tableau. So this is a certain type of Young tableau where in the vertical direction, so the elements are strictly increasing like this. But there is no restriction on the horizontal relations. Okay. So the semi-standard Young tableaus is a very famous Young tableau. So in this case, so the element is non-decreasing in the horizontal order, but in this case there is no restriction. So for example, so the element can decrease like this 4, 5, 3, and so on. Okay. And we also define the energies of this tableau, which is related to the theory of crystals in quantum group, like this. So and this kappa is a certain sequence of non-negative integers like this, and the nu is the partition like this. And on the other hand, so on the right-hand side, the PQ is a semi-standard skew Young tableau like this. Okay. So actually, if you establish this relation with these properties, so we can easily get this refined Cauchy identity. Okay. Because in some sense, so these objects are the building block of these factors in the Cauchy identities. Okay, like this. Because from V and W, so we can construct the q-Whittaker function like this. So this is the result of the Sanderson. This is something Demargioule character formulas for the q-Whittaker function obtained by Sanderson and Searing Tingley and other peoples. And so and the kappa is a certain building block of this mu, this factors, and this p and q. From p and q, so we can construct a skew Schur function like this. Okay. So in this sense, so from this bijection, so one can get the skew Cauchy identities. Okay. So I'm boring about the time, but sorry, I want to explain a little bit about how we get this type of bijections. So to obtain this bijection, so we introduce the certain time evolutions of the pairs of skew Young tableau. Okay. So based on a bumping algorithm of the RSK correspondence like this. Okay. So but this time evolution has a very special features. Okay. Because yeah. So let's focus on the these elements. Consecutive positive element, column by column. In this case, in this case, this, and this. Yeah. And actually, so these objects can be regarded as a soliton. Something a discrete analog of the solitons. Okay. So because if these solitons are far apart, so okay, so the solitons with length k, so go downwards, with k step, downwards by k sides. So this means that so the solitons with length k, so had speed k. So if time goes by, so the soliton with the longer soliton, so catch up the shorter soliton, and if this happens, okay, the soliton structures collapse like this, okay, like this and like this, because in this case, so 3, 2, 2, 1 structure, but in the intermediate time, this structure disappears. Okay. This is 2, 2, 2, 2 structure. Okay, but the time, as time goes by, further time goes by, so these type of the soliton structures reproduced in reverse way. In this case, 3, 2, 2, 1. But as time goes by, the time, sufficiently goes by, the 3, 2, 2, 1 structure reproduced.
How do the two interact? You have this pair of. How do they interact as these two?
These two, that's I don't explain in this slide, but some certain combinatorial way. Sorry. So this structure is very similar to the so-called box-ball system. Okay, and so we expect a certain nice algebraic structures behind this time evolution, these dynamics. And so as in the case of the box-ball system, so we introduce the certain operators E and F, so which is called the Kashiwara operators, and we equip the affine bicrystal structures on this space. Okay, and these operator E and F, so can commute with the RSK time evolution like this. Okay. So by using these structures, so we have by using structures, so we find that there are two ways of looking in this dynamics. The first one is the skew RSK dynamics itself, but this is very something a complicated dynamics. So complicated interaction of the solitons. But so by using these structures, so we see that for every pairs of the skew tableau, so we can go to the certain so nice pair, so whose dynamics is very trivial, okay, whose dynamics is linearized. So there are two ways of looking. So the red path, and which is non-linear dynamics, but the light, so the blue path, which is a non-linear dynamics, and the red path, which is a linearized dynamics. So from blue, this time evolution of the blue path can be completely characterized by the skew partitions, the skew tableaus. On the other hand, so these linearized paths can be completely characterized by this combinatorial object. So this is the this is very rough, but so the essential stories.
So you say that this is the equivalent of the lax pair on the left, or the something when you the left part. Sorry, right part. I mean the T0, T0, T1, T1. It's a lax pair, or it's related to that when you simplify the
lax pair.
No, it's not. I don't know. I was just wondering because sometimes.
The T0 is a certain skew tableau.
Okay.
Yeah.
So it's
with
not
some,
an analogy,
yeah.
it's,
Yeah. Sorry. Yeah. So. Okay. So this is some certain rough stories about this. Yeah. And okay. So in the Littlewood case, so we can do the similar things. How many time? How much time?
10 minutes.
Oh, 10 minutes. Okay. Yeah. So we get okay. Yeah. Sorry. Yeah. So yeah, we can do the similar things. All right. About this, this relation like this. Okay. So so equivalent relation of this refined Littlewood identity is a certain relation between a marginal distribution on a two probability measure. That here, the left-hand side is the half q-Whittaker measure, so which is related to the KPZ model in the half space. So in the Q push tase with particle creation is related to this one. And the left-hand side, so is the probability measure on the right-hand side. Sorry, is the free boundary Schur measure, like this. And this is a Pfaffian point process. Okay, so from this relation, so we get a nice Pfaffian formula for the KPZ model in the half space. Okay, so this is the result. The right-hand side, the left-hand side is the probability distribution of a certain q-generalization of the push tase step with particle creation. The x nt is the nth particle position at time t in the q push tase step with particle creation. So this probability distribution is expressed as a Fredholm-Pfaffian form like this. Okay. So where the correlation kernel L is the 2x2 matrix kernel, like this. Okay. But it looks a little bit complicated, but these expressions can be useful to analyze the asymptotic. Useful to do the asymptotic analysis. Okay. So by using this formula, so we can actually, consider the KPZ equation in half space. So this is our goal of this study. So we again consider the KPZ, one-dimensional KPZ equation, but in this case we consider that x is only on the positive region like this. Okay. And on the origin, so we put a boundary parameter omega like this. Okay. So the problem of well-posedness has been proven by these peoples. And there is a Kohl-Hopf transformation like this. So under these transformations, so the KPZ equation can be transformed to the stochastic Hito equation on the half line, like this, with certain boundary condition here. Okay. So and the solution of Z can be expressed as this form by the Feynman-Katz formula like this. Okay. So yeah, and this expression so can be regarded as a partition functions of the random directed polymer. This. So so the main result is that the certain Fredholm-Papian formulas about the probability distribution of this quantity. Okay, but this quantity, so we are interested in this quantity, okay, because so we expect something interesting transition phenomena like this. Okay. So in this case, omega here is the boundary parameter. Okay. So the omega appears in this form like this. Okay. So, but if the minus omega is large enough, so the configuration that the polymer is pinned, the Brownian motion is pinned at the origin, so has a dominant contribution to this quantity. Okay, and in this case, the fluctuation so is expected to be Gaussian, and the fluctuation scale is t to the 1/2, okay, because it is a one-dimensional like, and so the situation that central limit theorem can be available like this. But if the boundary parameter is not so large, okay, so not only this contribution but also the infinitely many configuration can contribute to this quantity, okay. And in this case, the fluctuation should be KPZ like, and the time scale is not 1/2 but 1/3. Okay, so we expect that there is a certain transition with respect to the boundary value omega. Okay, so and this is a result like this. So okay, so the omega is minus 1/2 is a critical value. Okay, so if omega is larger than this critical value minus 1/2, or the minus omega is smaller than 1/2, so the fluctuation becomes a KPZ like, and the distribution becomes a GSE Tracy-Widom distribution. Like this. On the other hand, if minus omega is larger than 1/2, or omega is smaller than minus 1/2, the fluctuation becomes a Gaussian like this. Okay. So, and at a critical point here, so the fluctuation becomes a GOE Tracy-Widom distribution. Okay. This type of transition is called the Bike and Range phase transition, like the Bike and Range transition. So, like this, and it is so we believe that it is a first mathematically rigorous derivation of this Bike and Range transition in the KPZ limit of the half space. Okay. So,
do you have any intuitive explanation why GOE appears at this criticality?
GOE is it's a little bit difficult, but the reason why intuitive the GSE appears is that because so this is we consider the probability measure on the paired partition like this. So the GSE is appeared. The GSE Tracy-Widom distribution is the largest eigenvalue distribution of the GSE random matrix, and GSE random matrix has some mathematical structures that so the eigenvalues has twofold degeneracy. Okay. This situation is similar to the probability measure on the paired partition. Okay. So in this case, GSE appears here. Oh, sorry. This one. In this case, GSE appears. But if the boundary parameter is large enough, so So one element of the partition becomes very large compared to other partition. And in this case, a Gaussian appears. And the critical point is GOE. Yes, so this I cannot explain this. Okay, right. Sorry, I take time. And so I briefly explained the outline. Okay, so this is a Q push TSEP. So this is the final result by range distribution, and this can be so. And at the top level, so we get the relation in the discrete level. So and we take a Q equal 1 scaling limit and certain continuum limit. So we get a stochastic. So this relation goes to the this relation. Okay. So this is the stories of these derivations. Okay. This is let us summarize my talk. So in my talk, so we have a certain refinement of the Cauchy identities and refined Littlewood identities, and using this, so especially using the Littlewood identities, so we get the bike range transition in the KPZ equation in the half space. Okay, so thank you very much for your kind attention.
Are there any questions? I was wondering, you consider this KPZ equation with some boundary, which is related to the Neumann type boundary, I think. And at the level of the totally asymmetric double exclusion, you can go from the totally asymmetric to the KPZ equation. So I was wondering, for this microscopic model, what would be the type of analogous boundary condition?
Oh, in TASEP.
Yes.
Yeah, I think there is a certain we consider the TASEP and something certain the TASEP on the half line and so the particle there is a boundary source at the origin and the particle can enter with certain parameter gamma like this.
And how is it gamma related to omega?
That's. Basically, how?
Because it's, you have this critical value, so there must be some relation at the level of the boundary. It's 1/2 omega, 1/2. I was wondering how it.
Half omega. Sorry, I cannot answer.
Okay. Are there any other questions? If not, we just in time for the break, so we have another question. Oh, sorry.
Oh, sorry.
Can you explain the transitions to the half space log gamma polymer?
Yes, because so to get to get this result, so we go through the half space log gamma polymer. And we can show the Viken range distribution at the level of the half space log gamma polymer. Thank you.
Okay. Well, thank you and.